back at the English sentence. You also don't use the words. For every language, what Google does now is it takes 32,000 fragments. So for English, for example, the would be a fragment. This is very common. In would be a fragment. Something like Socrates wouldn't be a fragment. It would be sort of so and cra and t's probably, I don't know. So morphemes will be fragments. Individual letters will be fragments. And so now you don't have any unknown words in the sense that you can always make a word out of these fragments. And it just takes the 32,000 from these fragments. So as you're allowed 32,000 fragments, you have to make all English words out of them. What fragments do you want? And that's just automatic. So that doesn't involve a linguist. You then feed these fragments into these paired encoders and decoders, and you just learn everything from the data. And you do not put in any linguistic knowledge at all. You don't put in the rules of English grammar if you're learning English. It turns out if you're trying to translate Chinese into English this way, you don't have to speak Chinese, you just need this database of matched pairs. So there's basically been a rule around for a long time among machine learning people, which goes like this. If you want to make your, well, this was really for speech recognition, it was a guy called Fred Jelinek first proposed this rule. He said, every time I fire a linguist, my speech recognition system works better. So, this machine translation system, linguists are involved in collecting the data. Linguists are involved in telling you what the names of the languages are. But basically, in the guts of it, in figuring out what the weights are so that it actually works, no linguists, just data. And linguists really don't have that. We're trying to figure out how to use a negative number of linguists, but we haven't figured it out. Okay, this is very bad news for linguists from some time ago, like Chomsky, who insisted that language is innate and you couldn't possibly learn it from data. So now all of Google's translations are done this way now. It does about, I think it does about 2 billion translations a day this way. And nothing innate. It's utterly non-innate. There's data and there's these random initial weights. Chomsky could not have got it more wrong, at least for this kind of system. And once you've seen it work for this kind of system, all those arguments about how people couldn't possibly learn it seem a bit thin. Okay, I'm going to now connect those two things together before I say a bit more about what faults are. So for machine translation, we feed in a sentence, we get a thought vector. If you ignore the attention aspect of it, we then take the thought vector, we feed it to a decoder, and we get a sentence in another language. Initially, we used language-specific encoder, so you'd use the English encoder. If you're learning French, you'd use the French decoder. People later discovered that it works pretty much as well if you have one encoder for all languages. So what you do with this encoder is you put in the language. It will identify the language. You don't have to tell it the language. You tell it, you give it one extra symbol, which is the language that you'd like it to come out in. And then the decoder network, which is now the same for all languages, takes the thought vector and decodes it to the translated thing in that other language. What's more, when you train this, you train it on lots of different language pairs, but you can hold out a particular language pair. For example, you can never train it to translate Turkish to Korean. So it's never seen a pair of Turkish and Korean. It will have seen sort of Turkish and Chinese and Turkish and Japanese and Turkish and Finnish, and it will have seen English and Korean and French and Korean and Hungarian and Korean, but it will never have seen a Turkish-Korean pair. The first time you showed a Turkish-Korean pair, it translates it right. And that's because it's going via this intermediate thought vector, which really is capturing the thought. That's capturing what the sentence means. And once you've got what the sentence means, That's more or less language independent. Now, there's a lot of cultural insensitivity there, because of course, the fine meaning isn't the same for different cultures, even for English and French, which aren't that different. You can't exactly translate, but we're just going to ignore that. Okay, so now, since we can do machine translation, now we can ask, instead of the encoder, why don't we use an image? So what we're going to do is we can take the image, we're going to run it through that neural net, which we trained to recognize these 1,000 different objects. And the last layer, just before the output is sort of making bets on the different classes. Just before that, you have a high-level representation of what's in the image. And you know the high-level representation has kind of got at the kinds of objects that are out there. And it has to have got at all of the kinds of objects, because you don't know which one was named. And so you take that representation, I'll call that a percept. And instead of feeding in a thought, you feed in a percept. And you ask it to decode that as a linguistic string. Okay? And to do that, you train it on percepts coming in and getting decoded to strings. So you need a database. Microsoft kindly supplied 200,000 images, each with several different strings that describe it, several different captions. And you just train it on that. So to begin with, they didn't retrain the perceptual thing. The perceptual thing was trained to recognize objects. They just take the top level of that just before the output and say, let's substitute that for a thought vector, and now let's just decode that into words. And this answers the problem of how do you know what the neural network sees? Now, if you're philosophical, you think, well, the neural network doesn't have consciousness, so it doesn't see anything. Or you think the neural network sort of sees things very different from us, and so how will we ever know? Or you just train the neural network to tell you what it sees, and it tells you what it sees. And whether you believe it or not is up to you. But it's the same with a person. When a person tells you what they see, they're often talking rubbish. They have no idea how their vision works, and they will tell you all sorts of things that can't possibly be true. Actually, I have a favourite imagery task that goes like this. Some people claim to have very clear mental images where they can see things vividly. And so I want you to imagine the following thing. We've got a checkerboard, and the checkerboard has blue squares and yellow squares. Okay, the squares are blue and yellow. And this checkerboard disappears into the distance, getting smaller and smaller until it's just a dot. And I want you to imagine that. When it's just a dot, what colour is it? And many people will say green. And green is what you get when you subtract colours. You're adding colours here, so it should be grey. So people will tell you what they see in their imagination, and it's nonsense for many people. Okay. The honest answer is, actually, when it got really small, I couldn't quite see what I could see. So, if you then showed a picture like that, which is never seen before, this is a test picture. In the database, it's people are crouched around in an open market. That's the correct answer according to the database. This is what the neural net says. And this isn't as good. It hasn't got the crouching of the people. But it does understand it's an outdoor market, and they're doing shopping. And it's sort of up for grabs how much it really understands. But at least it produces that string. And here's the one I showed you at the beginning. So you now have some idea how this can be done. And in the database, it says a young girl asleep on the sofa cuddling a stuffed bear. This is less good, it's less detailed. But a close-up of a child holding a stuffed animal is pretty good. And much better than you could do with symbolic error. You may have got the idea by now, I don't really like symbolic error. So, because I do neural nets, I know that if you want to get the neural net to learn something, you just go over the data again and again and again and again, and each time it changes the weights a little bit, and eventually it learns it. So, once more, thoughts aren't like symbolic expressions. They're big patterns of neural activity. They're caused by strings of symbols, and they cause strings of symbols. And so we can refer to them by using strings of symbols. But to mistake the thought, for the way you refer to the thought, is crazy. It's as silly as thinking that because when I show you an image, I show you a bunch of pixels, your representation of the scene in the image is a bunch of pixels. Your representation of the scene in the image is a much more interesting, complicated thing. It's nothing like pixels. Okay. And now I want to finish by showing you how you can do analogical reasoning with these big vectors. I'll do it with word vectors rather than thought vectors, but the same kind of arguments apply to thought vectors. So let's start with a forced choice. I'm going to get you to make a forced choice between two propositions. Young children don't necessarily know that these propositions are both wrong. You understand perfectly well that these propositions are obviously wrong because you understand a little bit of biology. But you also know which one is more correct, at least in our culture. So in our culture, it's very clear that dogs are male and cats are female. And that's because dogs are big and stupid and make a lot of noise and chase after and cats are kind of smaller and subtle and always come out on top. Okay. So logic can't explain that. I mean, if I ask you, what's the logical argument that says that the second one's better than the first one? Because you don't do reasoning to arrive there, it's just immediately obvious that dogs are male and cats are female. And it shows up in our language all over this. But if you've converted cat into a big feature vector, and you converted dog into a big feature vector, and you converted man into a big feature vector, and woman into a big feature vector, you can just look and see which feature vectors are more similar. And you'll see in those feature vectors that it's obvious that cats are female and dogs are male. So one thing we can do is, after training a neural net, and this was a neural net that wasn't trained for translation, it was just trained to predict the next word in Wikipedia. So we're going to train a neural net to predict the next word in Wikipedia, and we're going to train it on a lot of words, like 500 million or something. And then we're going to look at the word vector of this word. And we're going to take the 2,500 commonest words, and what we want to do is produce a plot in which very similar word vectors are very close to one another. We want to do that in 2D. And these are going to start off as like 100-dimensional vectors. And if I show you 100 dimensions, well, I can't show it to you, and you wouldn't be able to make sense of it anyway. So what we need to do is take these 100-dimensional vectors and somehow squidge them down to 2D in such a way that things that are very similar are very close together. We don't care so much about things that are very different being this far apart or this far apart. What we care is that similar things should be close together. Many of you will know a method called principal components analysis, which people will tell you is the best way to, if I've got 2 dimensions, it's the best way to display the data in 2D. It's one of the worst ways, because what principal components analysis respects is the big distances. Principal component says, I've got to get the big distances right. I don't care a hoot about the small distances, because I'm dealing with squared errors. Forget the small distances. I want to get the big distances right. We want to do the opposite. We want to get the small distances right. So there's a method called t-SNE that will get the small distances right. And if you take all those words and you plot them in 2D, they look like this. Oops. Like that. So if you just look at the structure there, you can see there's clusters. And there's clusters within clusters. But it's not they're not uniformly spread out over space. And I'm going to show you the clusters in those red rectangles. So let's start off with this cluster here. That's clearly, there's a tight cluster there and these are words that are somehow similar. And it's learned this just from trying to predict the next word. So as far as the neural net was concerned, it was getting this sequence of uninterpreted symbols. All it has to do is predict the next symbol. But in order to do that, it's converted the symbols to feature vectors, and the feature vectors tell us a lot. So let's look at that red rectangle. That's what it looks like. I hope you can read these. Here's Scotland, England, Wales, Ireland, and Britain. Here's Canada, down by Australia. Here's Toronto, it's up here somewhere. Yeah, Toronto is sort of near Detroit and Boston, not far from Sydney and Melbourne. A bit further away from Montreal. So this isn't geographically accurate. But notice Quebec is down with Berlin and Paris. And notice that Vietnam and Iraq are almost identical. So people could have saved a lot of trouble if they noticed that. But of course, the strings of words that were modelled here were after the Iraq War, and that's why Vietnam and Iraq War was identical. Okay. I like this one. I went to Cambridge, and it's obvious what should be underneath Cambridge, and it is. It's practically identical, but it's clearly underneath. So here's another piece of it. You'll see here, these are sort of fancy aristocratic things. These are sort of university kinds of roles, like student and teacher and master and professor and author, and also musicians. You'll notice that the thing closest to legend is guitarist. But the thing second closest to legend is engineer. We're closer than professors. And you notice a lot of sensible things, like these are political positions, these are military positions, these are professions. And so there's a fellow there who's senior and junior. Let me show you one more. I'm just trying to give you the idea that just by trying to predict the next word, it's understood all sorts of things about what these feature vectors should be like. That's captured a huge amount of knowledge in the feature vector. And that's going to allow you to do reasoning with these feature vectors. Here's from the middle there. I like this one. It's got tropical, wild, dark, magic, evil and dead all together. It's got colours here. But that's kind of... Well, it's obvious that they all go together, right? This is part of another cluster, and you'll see this is clustered mainly, there's syntactic clustering here. These are all adverbs. It's got largely, primarily, mainly, mostly. It's got probably, possibly, perhaps, which maybe isn't an adverb. So it's got very sensible things near one another. Entirely, completely. So now, given that the vectors look like that, we can now do reasoning with these vectors. So here's a classic analogy. Paris is to France as what is to Italy. Good. Thank you. Maybe you looked at the bottom of it. Very impressive. Nobody got it wrong. And the neural net gets it right too. And here's how the neural net does it. You take the word vector, so this will be like a 100-dimensional vector for Paris. Here it is. And you take the word vector for France and you subtract it. So we subtract this vector from that vector, and then we add on this vector. So what we've really done is we've added on the difference between France and